hour. A lot of this, if you're just glancing through the note sheet I provided to you, a lot of this is just information we need to discuss to make sure you understand. This isn't all examples. And we just did not get to the last two examples. In second hour, I wanted to leave enough time for the homework quiz, so that may happen in this hour as well, and that's fine. We can quickly pick up with those before we move on for tomorrow. But as a reminder for this week, so today and tomorrow we are reaching the halfway point of Chapter 5. Wednesday, that means we are just reviewing 5.1 through 5.4. And Thursday is a summative quiz. So today is the only homework quiz. Thursday is a summative quiz. So that means if you are gone Thursday and you are also going to be gone Friday, talk with me so you're not coming back Tuesday, January 2nd and having to make up a quiz after break. So 5.3 is on polynomial functions. And so this first part is being able to identify what a polynomial function is. We're coming back to the idea or definition of the degree of a polynomial. We're also introducing the leading coefficient. And then finding polynomial function values, which is something function values you've already done. This is just specifically for polynomials. So first of all, at the top, a polynomial in one variable is an expression of this form. This form, I realize, looks maybe very complicated. It has a lot of a's, x's, n's. But what I want to point out to you, so a polynomial in one variable, x is the variable here. X is often the variable. It doesn't have to be. So x is the variable. The a's are all representing coefficients or constants. And then the reason they're using subscripts on the a's is so they don't have to use a different variable for every coefficient. So notice, like for the first term, the subscript on a matches the exponent. So if you have a sub n, that is going to be the coefficient for the x to the n term. More specifically, like a sub 2 is the coefficient for the x squared term. That's just how to interpret that formula they're giving you. It's not a formula you need to have memorized by any means. And that's what this explains. All of the a's are coefficients. They're real numbers. And then n, all of your exponents have to be non-negative integers. So all of your exponents have to be 0, 1, 2, 3, 4, or so on. No negative exponents. No exponents that would be decimals or fractions. Those are not polynomials. We've talked about some of those ideas already in this chapter. And then I've already referenced this, but a polynomial is in standard form when the values of the exponents on the variables are in decreasing order. So I just talked about that actually reviewing how to set up the division. And the following is reviewing what the degree of a polynomial is and then the leading coefficient. So the degree of a polynomial, we've already technically defined this, but when you only have one variable, the degree is the value of the highest or the greatest exponent. And then we have not talked about what a leading coefficient is, but the coefficient of the first term of a polynomial in standard form is called the leading coefficient. You can also just think of this as the coefficient of the term that has the highest power. That would be the leading coefficient. So what this gives you is some polynomial expressions. Some polynomials, based on their degree, have specific names. Some we've already learned about in different chapters. It gives the degree and the leading coefficient. So the first one, the expression is just 12. Can I have it quiet, please? Realize if you're talking quietly, when there's more than one of you talking quietly, it's still loud, and it's rude. The expression is 12. This is just a constant. There's no variable. You could, though, if there was a variable, think of this being 12x to the 0 power. So the exponent would be 0, and so any constant is a polynomial with a degree of 0. And then the leading coefficient is just the number. So then the next expression, it gives 4x minus 9. The exponent on x is a 1, so it is a degree of 1. We've already learned about these types of expressions or these types of polynomials. These are linear. So we had a whole chapter just on linear functions, and that would be a specific polynomial of degree 1. The leading coefficient, the coefficient of that term is 4. And then when your highest exponent is 2, as in the next expression, so that degree is 2, and that is a quadratic expression or a quadratic function. We've already spent an entire chapter on quadratics. That was chapter 4, so we've already learned about those polynomials. And then the leading coefficient, the coefficient of the x squared term in that case is 5. And then when your highest exponent is 3, so the degree is 3, and then this also has a specific name. We haven't formally talked about these, but that would be a cubic function or a cubic polynomial. And that leading coefficient in that expression is 8. There is a specific name if you have a degree of 4. It's a quartic, 5 is a quintic, and then eventually if you just say polynomial of degree 3, of degree 6, they're referred to in that form as well. So some have specific names. Am I requiring you to know the specific names? No, but if I say quadratic, you should know what that means. If I say linear, you should know what that means. And then it does give the general expression again. This highest exponent is n, so it lists the degree as n. The coefficient of that term is a sub n. That would be the general form. So in the first example, you're just stating the degree and a leading coefficient, but if it is not a polynomial in one variable, to explain why, because in that case you don't need to find the degree or the leading coefficient. So if we look at A, we have 7z cubed minus 4z squared plus z. We only have one variable, z, so it is a polynomial in one variable. What would you say the degree is? 3. So no calculations. The highest exponent is 3. That's the degree. And then I'm going to abbreviate leading coefficient with LC. What do you think the leading coefficient is? 7. The coefficient of the term that has z cubed. So this happens to be in standard form. The powers of z are decreasing. So we are looking at that first term, but this is the term where you're finding your degree and your leading coefficient. Okay, so then for B, we have 6a cubed minus 4a squared plus ab squared. So this one, it is a polynomial. However, it's not a polynomial in one variable because we have two variables, a and b. So all we would say for this one is it is not a polynomial in one variable. And it might seem silly to explain why, because the explanation is there's more than one variable, but I'll say, because it does ask you to explain why in the directions. So, because, I'll say there are two variables, a and b. So it's still a polynomial. We could still find the degree, but the polynomial functions we are working with will just have one variable. So we're not really concerned with polynomials of this form in these next couple of sections. And then example C, we have 3x to the 5th plus 2x squared minus 4 minus 8x to the 6th. So here we are back to just one variable. What would the degree be? The degree is 6. Leading coefficient would be negative 8. So even though this one is not in standard form, because the term with the highest power is at the end, not at the beginning. So even if it's not in standard form, you're looking for the highest power for the degree. The coefficient of that term is the leading coefficient. So if you were to write this in standard form, this term should be first. So I would have to write it as negative 8x to the 6th, and then the rest of the terms were actually in order. They just should have been after. So then I would have plus 3x to the 5th plus 2x squared minus 4. So make sure you understand what standard form is. If I ask you to write something in standard form, that you're able to do it. I know the directions here didn't say to do it, but knowing what that is important. So questions right now on standard form, leading coefficient, degree. Okay, so then the next part is actually now evaluating. But this, I guess, short paragraph before example 2 just explains more detail on polynomial functions before we had polynomial expressions. So a polynomial function is a continuous function that can be described by a polynomial equation in one variable. So it gives an example. So notice you have the polynomial expression, but it's f of x equals that expression. F of x is just y, function notation. They're calling this a cubic polynomial function because the degree, the highest exponent, is 3. And then it also gives more information about polynomial functions. It gives the simplest polynomial functions are of this form. F of x equals ax to the b, where a and b are representing numbers. So an example of that would be like if I had 3x squared. That would be a polynomial, a simplest form of a polynomial function. Those are called power functions. So when they just have one term, it's a power function. That's just more detail on polynomial functions. But example 2 is where we actually get into evaluating these. So it says the volume of air in the lungs during a 5-second respiratory cycle can be modeled by, and it gives a function v of t, where v is the volume in liters and t is the time in seconds. Find the volume of air in the lungs 4 seconds into the respiratory cycle. So I would like you in your groups to do this example because you've done problems like this already. This is just specifically telling you it's a polynomial function. Use that function you're given to answer this question. And we'll just make sure that we all know how to do it and all can get the right answer. So this example is kind of checking 2 things. 1, you know how to use the function to find the answer, and 2, that you're following order of operations correctly to actually get the correct answer. Yeah. Yeah. All right. I just want to make sure, I think, checking in with everybody, you at least knew that you needed to substitute 4 in for t. Now just make sure you did it correctly. This should be the final volume, 0.756. So if you were not getting that, that could just be how you're following order of operations. You would need to do the exponents on the 4s first, and then multiply, and then add. What would the units on the answer be? 0.756 what? Liters. Because you are finding volume. Okay, so are there questions on that one? Okay, then the next example is also working with function values. However, your answer is not going to be a number because we're not just substituting a number in. So I'm going to read through this and then point out a couple things. So it says find b of 2x minus 1 minus 3 b of x if b of m is 2m squared plus m minus 1. So I'm just going to highlight here, this is what we're trying to find. And then it says if this is a function we are given. So we are using that function to find the rest. So one thing I want to point out, and this is where when you are working through problems, you have to be able to identify what exactly is happening. This here is not b times 2x minus 1. You are not distributing b. I know that's what it looks like. How I know that that's not what this is it's giving me a function b of m. This is not b times m. So this is a clue to me that this 2x minus 1, that is going to be substituted into my function where the m's are. So the 2x minus 1 is going in place of the m into the function. Same thing here where it says 3b parentheses x. That's 3 times b of x is representing a function. And if I look at the b of m function, this means I'm replacing the m's with x in that case. So you are substituting quantities into the function. It's just you're not substituting just a number. So your answer is going to have x's in it. It's going to be an expression. I'm going to work through this in parts. So I'm first going to find the b of 2x minus 1. So rather than focusing on the whole thing, I'm just going to find the first part, the b of 2x minus 1. And as I already said, this means the 2x minus 1 is getting substituted into the function b in place of the m, in place of all of the m's that you see. So where I see 2m squared, I'm instead going to write 2 times in place of the m, 2x minus 1, and that's quantity squared. So the 2x minus 1 went in place of the m. And then plus, rather than plus m, I have to replace this m also with 2x minus 1. And then I still have the minus 1 from the function at the end. So you have already found function values even with variables. We've done this process already. I know it's just kind of building. This is more in depth than maybe you've done before, but you have, we've kind of explored this idea already in this class and in Algebra 1. It was first introduced. So now this is a matter of simplifying. So my question first, because we should start with exponents, how do we simplify 2x squared minus 1? Because I will say this, you cannot distribute the exponent of 2. You cannot do that. That would be incorrect. So what does 2x squared minus, or 2x minus 1 quantity squared, what does that really mean? No, the exponent is just on the 2x minus 1, not on this 2. So that 2 is just kind of hanging out right now. It means, so a power of 2 means it's multiplied by itself, like 3 squared is 3 times 3. So this means I have 2x minus 1 times itself. How do you multiply these? FOIL. So make sure with this, you are not distributing the exponent. You have to write it out to FOIL. So the 2 that's multiplied in front will stay. And then I'm going to write in parentheses what I get when I FOIL these. So multiplying the first terms, 2x times 2x is 4x squared. I'm going to combine the middle terms right away. So if I multiply 2x times a minus 1, that's minus 2x. I'm going to have another minus 2x with my outer and then my inner term. So altogether it's going to become minus 4x. So if you need to do that in separate steps, that's fine. I'm just combining it right away. And then a negative 1 times a negative 1 is going to be a positive 1. So I'm still going to have to distribute that 2 that's on the outside, but this would be the quantity 2x minus 1 squared. Then, I know I wrote parentheses around this 2x minus 1, and that's because I was substituting that quantity in, but you don't really need the parentheses because it's just being added. So when I rewrite this, I'm just going to rewrite it without the parentheses. So I have the 2x minus 1 and then the minus 1 after that. Continuing to simplify, then I would distribute the 2 to the 4x squared minus 4x plus 1. So that would be 8x squared minus 8x plus 2. And then I'm just going to rewrite everything. I'll just combine everything in the last step. So finally, once all the parentheses are gone, I can just combine like terms. So I have 8x squared. a minus 8x plus 2x would be a minus 6x. And then a positive 2 minus 1 is a 0. Those just cancel one another out. So altogether, the b of 2x minus 1, this isn't the final answer, but that part of it equals this. So I'm going to save that. That's going to be part of my answer. I'm just not quite to the place where I have to use it yet. So questions just on finding this first part on those steps. Okay, I purposely, as an example, picked one that had multiple steps. Not that every single one problem is like this, but just so you saw how to do a more challenging one. The next part then, because I know I'm going to have b of 2x minus 1 and then minus the 3b of x. So I'm going to find this piece, and then in the end, I can combine the two pieces all together. So the b of x piece, I talked about how this means, if you look at your function b of m, the m is being replaced with x in this case. And then that whole thing is being multiplied by 3. So the 3 I'm going to write out front 3 times. For b of x, that means in my function b of m, wherever I see an m, I'm just replacing it with an x. So I'm just changing the variable, basically. So I have 2x squared plus x minus 1. Then I have to distribute the 3. So that's 6x squared plus 3x minus 3. And then I don't have any like terms, so that part is already simplified. So then for the entire expression, because ultimately I'm trying to find this whole thing, so I'm trying to find b of 2x minus 1 minus 3 times b of x. And I already found these two pieces separately, so I can plug them in. So the b of 2x minus 1 was the 8x squared minus 6x. So I have 8x squared minus 6x. And then I'm subtracting 3 times b of x, which was the second part I found, the 6x squared plus 3x minus 3. And because I'm subtracting a quantity, I'm going to put that quantity in parentheses. I'll have to distribute the minus sign through. So minus 6x squared plus 3x minus 3. You could do that and then add them together. Yep. So then when I distribute the negative through, 8x squared minus 6x minus 6x squared minus 3x plus 3 is what I get, and then I just have to combine like terms. So I have 8x squared minus 6x squared, so 2x squared. Negative 6x minus 3x is minus 9x. And then I still have the plus 3. There's no like term with that. So this would be the final expression. Okay, I realize that was a lot of steps for this one. Again, they aren't all like that. You might just see something like b of 2x minus 1, and that's the whole problem. But questions on where either part came from, how it was put together. Okay. So you had an example of function values where you're actually just substituting a number in, function values where you're substituting expressions or variables in. I am going to stop here for today. I know it seems like we have a lot left. It's less than what it looks like because we just have to discuss the general shape and the zeros, discuss end behavior, and we just have the last two examples we can finish up tomorrow before we move on. I do want to point out, though, if you are interested in doing the practice, I personally would not do the practice for both lessons, save all of that for tomorrow. So you can still do part of this today. You can still do 15 through 33. The odds, that is practice just on what we covered. The remainder we'll cover tomorrow before we move on. But we are moving on and covering 5.4 as well tomorrow. So not saving it all for tomorrow would be wise.